So hi, hi everyone. Once again, I'd like to welcome all for the Pi Seminar series. Today we have with us Dr. Emmanuel de Bézenac, who's a researcher in machine learning, specializing in deep learning models for physical systems. He earned his PhD from Sorbonne University, focusing on integrating scientific knowledge into neural networks. His research on neural operators and hybrid modeling approaches has applications in areas such as fluid dynamics and climate modeling. After a postdoctoral position at ETH Zurich, he's joining INRIA. In fact, he has actually joined INRIA in 2024 to continue his work on data-driven methods for scientific machine learning. And so today he'll be talking to us on his work on the title, An Operator Preconditioning Perspective on Training in Physics-Informed Machine Learning. So over to you, Dr. Emmanuel, for rest of the talk. Thank you.
Yeah, thanks for inviting me. Yeah, so as you can see, the title's slightly changed, but essentially the idea is the same. So yeah, in this talk, I wanted maybe to So I'm sure all of you are familiar with PINNs, but I'm going to go quickly over them just for just to warm up. And so I'm going to present PINNs, and then mostly I'm going to present some theoretical results. So these results are not results from me. So there's been work on approximation errors, quadrature errors, and as we'll see in the following part of the talk, these theoretical results are quite nice, but in practice, actually, it turns out that the training error dominates. It's dominating the total error. So then, from that, we'll see some tricks and techniques that are used in practice to try to get the method to work. And specifically, we'll take a look at how these methods actually adapt the algorithm and and try to understand why they work and sometimes why they don't. So that's the general talk. So yeah, just to put things a bit back into the context. So how I see PINNs is in a bigger context, in a context where there's two domains that are brought together, the domain of physical modeling. So there's a totally different paradigm from the statistical machine learning paradigm. It's based on a deep understanding of the system, which stems from first principles. Then we derive PDEs. And these PDEs often are very difficult to solve. So that's one of the challenges. And maybe as a caveat for these methods, that they were not made to scale with large quantities of data. So on the other hand, we have statistical modeling where we don't.
Just one question. What do you mean by not made to scale with data?
Okay, so let's say like take you're gonna solve the Navier-Stokes equation in a particular regime, right? So then you're gonna simulate from some given initial condition, and then if you're in a slightly different condition, if your initial conditions changes by an ever slight amount, you don't know the solution of the Navier-Stokes equation. And you're not going to leverage your past simulations, and you have to simulate again to get an understanding. And so the idea is that if you simulated many times, even though you're not going to predict maybe exactly, even though you're in a slightly different situation, maybe you can use the data and the knowledge derived from the data to try to predict your condition. And so it's in that sense that it's not made to scale with data. This is what I mean.
Okay. Thank you.
By that. Okay, so yeah. So statistical modeling was actually made to solve these type of problems in this specific way. And turns out nowadays that it's very simple with PyTorch, for example, or JAX to develop and to prototype really, really fast and efficient methods. Okay. So here's where physics informed machine learning comes. So here we want to leverage the prior information that we have, the scientific knowledge, and extract knowledge from data, hopefully to make the best of both worlds. So in this, there's a certain number of challenges. Developing fast surrogate models, for instance, is a big one, or augmenting the physical model. So like maybe you have some unknown forcing terms that you'd like to learn from the data. So here the equation is still very, very helpful in these cases, and especially in cases where you don't have access to the full state and only partial observations. And this is like specifically a big thing in climate and weather applications. Okay, so physics informed neural networks. I'm not going to introduce them. Essentially, it's a good, nice way to combine PDEs and neural networks, and they're done. It's combined through the loss function, and initially was made to solve forward and reverse inverse problems jointly. So there's been lots of activity in this area, and specifically lots of people are just like developing, like for each equation you're going to show that this for a specific set of initial conditions, well, maybe the PINNs that is trained in this particular way it is going to work for your problem. So there's been really lots of problems, lots of people who tackled this. Of course, you know this probably better than me. So here, quickly, the setting is that we have access to this PDE, so where D is our differential operator, and U is our state, which is a function. We have some given boundary conditions. And on the other hand, we're going to have consider a neural network, U theta, parameterized by theta. We're going to have a loss function, which we're going to minimize with a gradient descent. And if our neural network sort of represents the ansatz of our PDE here, and we can formulate the loss such that the loss is when it's equal to 0, the neural network is a solution of the PDE. So here we're going to have this term here, which is the PDE residual, and B, which is the residual on the boundaries. Then hopefully, if we minimize this loss, then U theta is a solution of the PDE with many ifs. So okay, in practice, you all know this. We can't exactly approximate this integral in the loss function. So we resort to methods such as Monte Carlo, where we randomly sample points in the interior and on the boundary, and then we try to optimize this loss function, computing essentially these derivatives using AutoDiff. So this is what's done in practice, and in like PyTorch. Okay, this is probably not the best implementation, but here we can solve the very simple diffusion equation with just a few lines of PyTorch, and it sort of works. Okay, so in the initial, one of the initial papers solves the Burger's equation in a forward and a inverse setting for a simplified Navier-Stokes equation. Okay, so maybe yeah, so maybe I'm going to go maybe a bit in theoretical analysis of PINNs. And specifically, like if you're already aware of this, just tell me and I can skip it, or if you want me to go slower, don't hesitate to ask if you have any questions. Okay, so sorry, I'm just gonna move my thing here. Okay, yeah. So we need some theoretical guarantees. So that this is what we'd like. So once we run our algorithm, we want to be sure that our recovered ansatz here, u theta, is actually close to the solution. So this is what we actually want to minimize. But obviously, we never have access to the solution u. So we can't just minimize this in a straightforward way. But what we can compute is the PD residual over the whole domain. So this is going to be, so this is closer to what we can actually have. So this would be integrating over the whole domain, computing a norm for each point. So obviously, this is also an integral, which we can't compute, but it's closer to something that we can compute. And what we can compute here is the training error. So after doing this Monte Carlo estimation of the integral, we can approximate this. And so now this is the training error, what we're trying to minimize. So the question is, theoretically, can we find an ansatz neural network, u theta, such that when we make the training error, well, the quadrature error, or this sort of a generalization error, is small. So even though we enforce the differential constraint over a finite number of samples, does it actually translate to points over the whole domain? And so that's sort of like the first question. Can we find it? So this is more like of an existence thing. And so if we can't even respond positively to this, then we can't do anything. So now, if we can respond positively to this one, we can ask ourselves the second question, which is, if I make the training error small, does that imply a closeness to the solution? So these are two questions that I'm going to look at quickly here. And turns out that specifically for the first question, we can respond positively. So we can rewrite this quadrature error, because so f is equal to du. But so then we have this norm of du theta minus du, so the solution. And if we're able to, we can actually use some, if we have this bound, this is sort of like a coercivity type bound. So if we can bound this value by a constant that may depend on the solution times some Sobolev norm of u theta minus u, then we can show that leveraging the universal approximation theory in the context of a Sobolev norm, then we can show that we can find a u theta such that we can bound the Sobolev norm by epsilon, and then we can put epsilon over here, and then we can bound the overall quadrature error. And this is
just one question.
Yeah.
So this universal approximation theorem results given by Tim in 2021, is it only applicable for a certain architecture, or it is irrespective of the architecture? This is true.
Okay, so I don't remember exactly the details. I'm not an expert on this, but I think it applies very, very generally. In the case of so the universal approximation theorem normally from memory, the assumptions is that the activations are non-polynomial. And here I think it's the same thing. This is from my memory. I'm not sure.
Okay. Thank you.
So essentially what you're doing is that you're leveraging the approximation of for the pointwise values, but then you're also going to do that on the derivatives. So that's the general idea. If you can fit any derivative as well, then so I think it requires a bit of work, but it's an extension of the classical universal approximation theorem. So okay, so this coercivity bound applies quite generally, like specifically applies for linear PDEs, but also nonlinear PDEs in cases where U and its derivatives are bounded, and this was proven by Tim and Sid in 2024. Okay, so here we answered our first question. So it's actually possible to find a U theta that is close, such that the residual error is small. So then yeah, that's something that's already nice. Now we can ask ourselves the second question is, can we actually make if our training error is small, does that actually imply closeness to the solution? By using the same type of coercivity, where here we no longer have the subtle F norm, but just a simple L2 norm. But with this assumption, if our PDE satisfies this constraint, well, we can use the same sort of technique and just bound the solution, the closeness to the solution by a constant times the quadrature error, or the generalization error. So once we did this, we can use these are sort of, we can apply classical quadrature approximations, or like and we can bound the generalization error as a function of the training error plus some residual error, which depends on the method that you use, but also on the number of collocation points n that you're going to use here. Okay, so this is all very nice. We presented two ways to obtain generic bounds, and that are applicable in many cases. But there is a caveat, which is it's not necessarily informative, specifically if this constant is large, and this can actually be the case maybe if you're having a very nonlinear PD. And obviously, if you don't have enough collocation points, because then the bound becomes quite loose. And most importantly, if the training error is small. So here we saw that there exists a neural network such that the residual error is small, and a small training residual implies a small overall error. But now the central question is, can we actually make this training error small in practice? And this is what this talk is mostly focused on. So maybe it turns out that there is quite some difficulties to get the training error to be as small as possible. And one particular example is, just consider a very simple linear transport equation, where we have this constant velocity beta. And we can see that, okay, for small betas, so here we're in 1D. So here we have x, one-dimensional x, and here we have time. Starting by a sine function, we can advect this sign in time. And for small betas, on the left here, we have the ground truth. And on the right, we have the PINN solution. It's going to work for beta is equal to 10. But as soon as we increase beta to higher values, so values 30, we can see that we no longer satisfy this solution. And particularly, we can see this transport that's not, and the solution is not, or the initial condition is not able to propagate in time. So we're going to collapse to a trivial solution. So to solve this problem, there's a certain number of tips and tricks that are used, and I'm going to go through a few of them. So I'm going to go quite quickly. So one idea is curriculum learning, which is essentially, I'm going to start from, let's consider the same example, and I'm going to start by trying to solve a simpler problem, and then gradually I'm going to change the difficulty of my problem. This is why it's called curriculum learning, until I'm actually trying to solve my the problem that I had at hand. So to do this, you can make beta smaller, make the velocity smaller. We saw that it's possible to solve the equation in this context. And then we're going to do some training iterations and then gradually make a beta larger. So this tends to work, at least in the example of this paper. Tends to work quite well for beta is equal to 30. Another example, which is actually quite similar, is just instead of making the problem simpler by making the velocity smaller, we're just going to consider as solving the equation on a subdomain. So here the equation is solved for some given time, and we're going to consider the subdomain, just make solving the equation for a smaller time. So once we did that, it's possible to once we solved on this from 0 to delta t, then gradually we can solve it from 0 to 2 delta t, then to 3 delta t. And the results are actually quite similar to curriculum learning. Okay, so next, there's another one that's quite used in practice. It's called Fourier features. So instead of giving the coordinates as input to the neural network, before we're going to transform them into features, and these features essentially they're going to be sign-like features. So it's very simple. Then so here what we're going to do is we have x, our coordinate, then we're going to do a scalar product with some random value which can be learned or not. And this random value, yeah. And then this and then we're going to take the cosine and the sine of that and do that for lots of different random values. And so I guess the intuition behind this is that B is going to correspond to some frequency value. So in 2D, it's going to have two values. And yeah. Did you have any questions on this? I guess maybe you're familiar with this. I'm sorry, yeah.
Yes. One question here is that if I make this B matrix learnable, then how will that affect the optimization?
I mean, that's a good question. I don't think I can respond to it in a general way because it depends on the other layers that you have on the other architecture. So I don't think I can give you a response. But I think one intuition that you could have is always by just taking just a linear layer, a linear combination of these, and just doing gradient descent by learning the coefficients associated to this. And here you can actually write down what's happening. And I think you can sort of consider this as like a two-layer hidden neural network. And this is still quite hard to see, but I think there are some techniques that actually characterize what's happening. So what happens in practice is obviously that you can sort of shift your functions a bit how you like. So if you need to represent the higher frequencies, the hope is that you're going to be able to learn which frequencies you're going to learn. You need to learn, sorry. But in practice, I'm not sure it's done that much. Specifically, like if you're in low dimensions, it turns out that you don't actually need that many directions. Of course, the number of directions increases exponentially in the dimension, but if you're in 2D, sometimes you don't even actually you don't even need to sample them randomly. You just consider the Fourier series. So these can actually just be B is equal to 1, B is 2, 3, 4, 5, and just you go back to the Fourier series, and you can actually obtain. Then you know exactly which frequencies you're representing, and it's actually very simple. So yeah, I don't have an answer in the general case.
Yeah. Oh, thanks.
Okay, so once you have these features, you give them in the neural network. And then it turns out that in practice, so I think in this application, I'm not sure they're learnable, but I don't know if there's a very big difference between learnable and non-learnable in practice. And obviously, depending on your initial random distribution, which is set specifically towards, aimed towards solving problems at a given frequency. But if you were to just give the coordinates here, you're going to learn quite slow. You're going to learn the low frequencies first, and then it's going to take an exponential time to learn the higher and higher frequencies. But with Fourier features, you sort of change your ansatz and your implicit bias, and now you're able to learn high frequency functions quite easily. So this is used quite a bit in computer graphics and in different domains. Also a lot when you're in diffusion models when you're giving as input time, it's also used quite a bit. But these tricks are not entirely well understood. And why is that? It's because in order to understand these tricks, we need to understand the training dynamics to know why these tricks actually help training loss to go down. But as everyone knows, analyzing neural networks is notoriously difficult, and no one has a way to do that in practice, and I don't think it's coming anytime soon, but we can analyze this in a very simplified setting and then maybe have some insights based on this. And so this is what we do with Tim and Sid and Florent. So here's I'm going to lay down the assumption. So here we're considering a linear differential operator and linear boundary conditions. So linear boundary operator here, B. And so with a very simplified ansatz. So here we're going to consider like a sort of a Galerkin type discretization, where we're going to have some functions phi of k, which are going to represent our solution if we combine them linearly. And what we want to learn, our parameters here in this case, correspond to the coefficients associated to these functions. And we're going to see how this can actually be extended to neural networks in a very specific context. But this we'll enjoy the benefits of actually having tractable dynamics. And so the whole talk is quite informal, but I'm going to go a bit in the details, but not that much. but just know that it's made formal in the paper. And maybe if you have any questions, I can sort of guide you to which sections of the paper to look at. So now let's consider an instance of this setting, the Poisson equation, in one dimension with 0 boundary conditions. So here we're going to consider this forcing function, and the reason why we consider it this way is just because we know that the solution at the end is just going to be given to us by a sine of kx. So this is a very simple setting, but we can write down everything. We can write down the residual loss. We can write down the boundary condition loss. And let's consider Fourier features ansatz. So here, we're going to have an ansatz that looks a lot like the Fourier series, like the Fourier series, where here we're going to be learning the parameters, and our phi k's are going to be sines and cosines with the given frequency between 1 and big K here. So once we have everything, we can write down the gradient descent equations. So here we just consider gradient descent in its simplest form. And we can write, now we just have to compute the gradient with respect to the parameters theta of the residual loss and the boundary condition loss. So here, this is what we're going to do in this mathematically heavy slide. But I'm not going to go in the details, but just that you get sort of a gist of what I'm talking about. Maybe it's interesting to see the equations. So of course, in this context, we can bring the gradient in the integral, and then we need to compute the derivative here, and just using the chain rule or we can actually what happens when computing the derivative with respect to theta, we have a d star here that appears. So we're going to have the gradient of u theta applied to d star here, and this is a d star is going to be the adjoint of d, and like it's like in the finite dimensional case where d actually corresponds to a matrix that's applied to u. Then when you're taking the gradient of that, you're going to have this A transpose A, and this is exactly the same thing in this infinite dimensional context. Okay, so like I said, we're going to have this d star d, which is going to be very important. And we're going to have the gradient of u theta. So this, when you're going to compute it, it's actually just going to correspond to the different basis functions or evaluated at x. This is just because it's linear in theta. And then we're going to have this part here that's going to be totally independent of x. So then the gradient is essentially of the residual loss is going to look like this. So here is we're going to take all the coefficients and we're going to cram them into a vector, and then what we have here is this quantity. And in the Poisson case, as Rd just corresponds to taking the second derivative, since the second derivative, we take the adjoint of that, since it's self-adjoint, d square is equal to d, and then it just amounts to taking essentially the fourth derivative. So all this math is just a bit complex, but just bear in mind that this is going to be a square matrix, which corresponds to the number of different frequencies I have times the number of frequencies I have here. And the gradient of the whole loss is going to be this matrix, so this A res, multiplied by theta plus some constant. So, and this is all you need to know. So it's the gradient is equal to A res times theta plus some constant. Do you have any questions?
I have one. So I'm still not clear how you're coming to the second step. Uh, so how you are getting the gradient of u theta? Yes, there.
Okay. Yeah. So then, okay. So how I like to think about this is like in the finite dimensional setting where D actually corresponds to some matrix applied to some vector U. And so essentially what you're going to do when you're computing the gradient with respect to theta, you're just going to, it's just some chain rule. So first you need to do the chain rule with respect to this norm here.
Okay.
And then, so once you do that, you're going to have a 2 that pops out, which is going to be killed by this 1/2. And then you're going to take the gradient of theta with respect to this quantity over here. And here you're going to do the chain rule again. So you're going to compute the gradient of theta with respect to u times applied to the gradient of D, like with respect to the input, which is, since it's you're going to transpose that's appearing.
Maybe the way you have written it was confusing, but yeah, it's clear now. Yeah.
Okay. Yeah.
And just one thing, since you have written the final expression as a residue dot theta plus some constant, so basically this will only come when you have the Galerkin answers, right?
Yeah, exactly. So so here we have in all generality, we have this, which is equal to you can't reduce this. Yeah, this is, we're gonna, instead of having this phi, we're gonna have the gradient of u theta. And because it's linear, we can actually make this a phi appear on the right hand side, because we can rewrite our solution like this here. And this is not possible if our function is not linear in the parameters.
Okay.
But that being said, it doesn't mean that since it's a Galerkin discretization, it's linear in the parameters, but it need not be linear in the coefficients x.
Yes.
And then we'll see that actually with this insight, we can actually link this to neural networks in infinite width in a certain NTK regime.
Okay. Thank you.
Okay, so yeah. So now we can actually compute exactly what this matrix is in practice, because it's very nice. We have these phis. It forms an orthonormal basis. And so essentially, we're going to take the elements of the basis. We're going to apply the fourth derivative onto them. And then we're going to have this k to the power of 4, which k corresponds to the frequency. We're going to take the frequency associated to the sign, take it to the power of 4. And then essentially what we're going to have now in this matrix is going to be a very simple diagonal matrix, where the diagonal entries are going to be the frequency to the power of 4. So from the frequency 0 to the frequency big K, or minus K to big K. So this is just to give some simple insight. So, okay, so here we do the same thing. I'm not going to go into the details. We compute the boundary conditions. These are less interesting. And essentially what we can show is that the gradient of the total loss is going to be the same thing. It's going to be a matrix applied to our parameters theta plus some constant. And this matrix now is going to be formed by the sum of both induced matrices. So this big matrix here, and then this rank 1 matrix induced by the boundary conditions. And we can actually now we can have an idea of so once we have this matrix, we have this linear form. And so our updates essentially are gradient descent equations. It's going to be we can express them exactly in this particular setting. Because it's going to be they're going to look like this. So here, I'm just rewriting everything, putting things back into the gradient descent equation, and this is what we have. Since this is obviously a linear iteration, we can actually prove convergence in the case where A is invertible, and we can actually have an idea on the speed of convergence, which is tied intrinsically to the this matrix A, and in particular its conditioning. So by conditioning here, I mean we take the biggest eigenvalue and we divide it by the smallest eigenvalue. So in this case, we can bound the iterate at step L, and it's the distance to the solution by a function of the distance between the optimal solution and its and the initialization, the random initialization of the parameters theta 0, times this quantity here, which depends on the condition number. And this is to the power of the iterate L. And so as a corollary, essentially, what happens is, okay, if we want to be epsilon close to the solution, this gives us an order of magnitude of the number of steps that we need to achieve an error of at most epsilon. And turns out that we need a number of steps which depends linearly in the condition number K of A. Is it clear for everyone here? Do you have any questions?
I think no. So you can go ahead.
Okay, great. Okay, so now let's go back to this working example. Let's consider the instantiation of the matrix A. And in this particular setting, it's actually provable that the condition number of the matrix. So here we have a 0 here. You could think it's a 0 eigenvalue, but then this is killed by the boundary conditions here. And we can still have an estimate of the total condition number, which is going to be bigger than big K, which is the maximal frequency that we're representing to the power of 4. Okay, so for some insight in this is typically if we have K is equal to 5 and we solve the equation 500 steps, then roughly, if we want to solve it again for 25 frequencies, we're going to need roughly 300,000 steps. And this is only for Poisson in one dimension. So this is very, very cumbersome in this particular context. So this is only for Poisson. Now we can think about different other linear PDEs. It turns out you can generalize this quite simply. And just here I'm omitting the boundary, but it's actually studied in the paper. But essentially the gradient dynamics are going to be governed by this matrix A. And we're going to go, we already saw that this matrix A is going to look like this. And in particular, we have this Hermitian squared operator D star D here. And this is actually the culprit. So it's quite difficult maybe to interpret this the eigenvalues of this specific matrix, but then we can take an operator perspective. So we can, by leveraging the duality, essentially the condition number of this matrix is actually equivalent to the condition number of an operator, and this operator is going to correspond to the composition of this Hermitian squared operator D star D and this T. And we're so this Hermitian squared operator in the Poisson case just corresponds to the fourth derivative in one dimension. And this kernel in this operator T is just going to be a kernel integral operator. So here we're going to have a kernel here that's appearing by taking the scalar product of these feature functions here with respect to x and y, where we're going to have a kernel appearing, and then we're going to integrate this kernel against a function. And in particular, in the case, in our case, like if this, if our basis is orthonormal, it doesn't even have to be a basis. Assuming that the input is in the span, then we can actually, this kernel integral operator actually just corresponds to the identity. And so from here, what we can see is that this conditioning here mostly depends on our architecture, our ansatz that we've given. And this part here mostly is the PD dependent. And in this context, we can see that conditioning is essentially governed by the conditioning of this Hermitian squared operator D star D. Okay, so here we're going once again back to our simple Poisson equation example because it's nice to see, and we can actually plot the condition number based on our number of Fourier features or the number of frequencies that we want to represent, and we can actually verify our theory. So here, this is the condition number. We have a log scale, and here are a number of Fourier features. And we can see that increasing, essentially the condition number is increasing as a power of 4, which exactly corresponds to the theory. And now we can see what's the impact on training in practice. And we can see that we converge exponentially faster for Fourier features with a lower frequency. And here, just forget about this for these here at the bottom for now. But here, even after like 200 steps for the maximal learning rate, we have an error of 10 to the minus 1, but even after 200 steps. So this is actually quite a lot. Okay, now we can look at another equation. Go back to our linear advection equation that we saw with this the same 2D version of the Fourier series, the Fourier feature basis model. And that we can see that here in theory and in practice, actually the condition number, the conditioning of our problem depends on beta to the square. And then we can actually verify this in practice because the loss behaves as such. And so this explains this difficulty in training that we had before. Because essentially the conditioning of the problem becomes much more difficult, and we can actually have a rate at which it becomes more difficult in this context.
Just one question. You may, I'm not sure, but have you tried this for nonlinear PDs too?
So here, no, we haven't tried this for nonlinear PDs. This is just theory and simple theory in the linear setting where things are already very difficult. So we didn't try to look at a more difficult problem. I think that there'd be more complications arising in the nonlinear case, obviously.
Okay.
Okay, so now, so far, like I said, linear PDEs, linear ansatz in the parameters. And the idea is like, how can we connect this back to neural networks? So it turns out that it's actually possible to connect it back to neural networks using the so-called neural tangent kernel. So this is some paper by Arthur Jagtap that was introduced in 2018. And essentially, roughly the idea is that we're going to take our neural network here, parameterized by theta k, and we can Taylor expand it around its initialization here. So where the Taylor expansion is performed with respect to the parameters and not the input. So what we obtain at the end is not a linear approximation, but it's just saying essentially that we're going to start from some parameter theta, and then our parameters are going to evolve in parameter space or linearly. So this is what it says. Okay, so assuming that assuming that the Hessian, this Hessian and the differential operator applied to the Hessian is small enough, we can actually consider this tangent linear model for our model, and then in the same exact way, we can write down the evolution of the parameters, which is going to behave as a linear, or essentially our theta L plus 1 is going to be computed from our theta L times some matrix here. And this matrix, we're going to have this A matrix popping up again. So essentially, we have the same exact results as in the linear basis setting, where our features here are just going to correspond to the gradient of theta applied to u. And our theta, our parameters, we're going to evaluate them at the initialization. Do you have any questions here on this particular setting?
No,
okay.
I don't see that.
Okay. So it turns out that this assumption is actually verified exactly for the linear basis. So, okay, this is what we expected, because it generalizes this linear basis, but also for neural networks in this specific NTK regime. So when
I have just one quick question. So when you say so you started with a linear basis, right? So if you see this ansatz, you can still write down your a general feed-forward neural network in the same way. The only thing is your linear basis will become an adaptive basis, right? And your theta k is basically the weights in the final layer.
Yeah. I mean, you can always write that there, but then you're not really capturing the complexity of the dynamics, right?
No, my question is, I mean, do you really need NTK here? Because eventually what NTK does that they assumes your width are infinitely, infinite, right?
Yeah. Okay. So what's nice about this NTK regime, it's that we can actually bring it exactly back to something here. So essentially we can how do I say this? We can link our neural network to a kernel method, right? And so this kernel method is going to be nonlinear in the function, but it's going to be in our coefficient x. But our dynamics, our learning dynamics are going to be very simple because it's a linear. We're going to look for something that's linear. So the general assumption is that here the Hessian is bounded and the differential operator of the Hessian is bounded. And this is true in when the width grows unbounded in the NTK regime. But yeah, you're right. There's other cases where this is not the case. And maybe like in practice, this NTK, it's actually going to involve in time, but maybe its evolution is small.
Okay. Thanks.
But then obviously the analysis is much more cumbersome. I don't think, maybe it has been done. I'm not aware of it.
Okay.
Okay, so this is also like I said, in practice, we do have the kernel that changes, and we can't do this initialization, and we because the Hessian actually does change in time, and it is small, but not equal to 0. So there is some change in the direction. But we can still say, okay, maybe it's not going to explain everything like generalization. We're not going to explain generalization, but the question is maybe it can still yield insights into the optimization and training difficulties. So like I said, we have the conditioning of our matrix. This is our discrete problem. We can actually is equal to the conditioning of this operator, D star D, composed with T. And essentially, T encodes the architecture, and this here actually exactly corresponds to the NTK kernel here. It exactly corresponds to it. And so based on this result, we can actually have an idea on the spectrum of this kernel operator. And turns out that in I think this analysis was performed on the sphere, that it's actually the eigenfunctions correspond to the spherical harmonics or something like that, and the spectrum actually for the residual value network decays very fast. So the frequency depends decreases as k to the minus d, the dimension of the hypersphere. So we can actually leverage all the analysis in the NTK setting that was done, particularly here. So it turns out that, okay, maybe so this is what I wanted to say. So now you can ask, okay, what's the difference between just learning a PINN, so minimizing the residual loss, and just doing let's say we had the solution and we would want to regress to the solution. This is like more like a neural operator type setting. And in this case, this neural operator type setting where we're just doing regression to the solution, what would be the conditioning of our regression problem in the neural network case, or even in the linear basis case? And turns out the conditioning would actually be related exactly to this kernel integral operator T. And this is why, since the spectrum decays very rapidly, and this also actually exactly explains why we tend to learn the larger frequencies first, and then exponentially slower the smaller frequencies.
Em, I have a question here. So, previously, I think you showed that the conditioning was dependent on D star D on the previous case in regression. So I think during that time, I think you did also mentioned that your phi needs to be like it has to be orthonormal, and because of that, your T kind of goes to identity. So your D star D is what is deciding your conditioning, basically. But here, you're just directly you're given that your conditioning is dependent on T, but does that mean your D star D is going to identity, or is it like the T is dominating over that?
Oh, yeah, good question. So yeah, so this in the neural network setting, it's true that this we're not in the orthonormal setting, and so this T actually becomes something that's different from identity. And the in the PINN setting, the conditioning actually depends still on this D star D composed with this T. But in contrast, in the regression setting, so when we're not trying to minimize a residual, so when we're just trying to regress to the solution, so we're trying to minimize the norm or the distance between u theta and u, the solution. Turns out that since we're never actually taking into account the equation, the differential operator D, the conditioning is not actually going to be dependent on D, and it's just going to be related to the conditioning with respect to the architecture.
Sure. Okay. So basically, so it's basically like a theoretical reasoning that you're giving for this, or is it so it's by theory that it suggests it is dependent on T.
Yeah. In this regression setting, actually you can so let's say you could consider exactly the same ansatz here.
Okay.
And just by instead of minimizing this, you'd minimize the closeness to the solution. Then you can exactly in the same way you can write down the equations. There's the same equations that are going to pop up, except that we're no longer going to have this D star D because yeah, right. So it's just going to be like U minus F essentially, and so the D is going to be identity. We can set it to identity
Because it's an operator that you're learning. Is that what it means? Because D is not there because you're actually trying to learn the operator itself.
Yeah, like yeah, in this yeah, so like this is a simplified example where I'm giving. So you'd have U theta and you try to make it close to U. So this is like doesn't make sense because if we had U, like I said, we wouldn't need to approximate it with U theta. But in this neural operator setting, it makes sense because we'd actually replace this D by some by like we'd have G of maybe U0, like would for time dependent problems would take like G this operator taking as input the initial condition or some associated input parameters associated to the initial condition, and then we tried to predict the solution. And then since the equation, we're never taking D the differential operator into account, the conditioning of the problem is not going to depend on the differential operator, but it's more going to depend on the conditioning of the architecture that is used for this operator G. I don't know if that's clear.
Yes, I mean, I would say it's maybe partially clear, but yeah, I mean, I think I can just take it offline. Yeah, but thank you. Yeah.
Just for to get the gist, it's like if regression is for me is simpler, and the reason it's simpler is that you don't actually have a differential operator because it's differential operators that they're quite hard to tackle.
Sure. Thank you. Maybe I can take a look into the paper. Like if you are like giving the citations later on, I can always read that. So thank you, sir. Thank you.
Yeah. Okay. Yeah. Maybe it's not explicitly written in the paper. But yeah, we can take it offline if you want. Okay. So yeah. So in contrast, yeah, we can say that if this differential operator, a general rule of thumb, or how I like to think of it, is it's not necessarily correct because it depends on spectrum of this operator T. But the more this differential operator here, D star D, is going to be complex, well, the harder time we're going to have to solve the problem with PINNs. And so now you can say, okay, you want this conditioning to be as small as possible, this condition number. Since you can't act on the PDE, so you can't act on the differential operator D, you can act on this kernel integral operator T. And this, we said that encodes the architecture. So if I change my architecture, then it's going to change my kernel integral operator. And then you can say, okay, what's the best model that I could choose? My best ansatz, and hence my best calligraphic T operator would be choosing T that is close to the inverse of this Hermitian squared. And why would this be the case? Because it's simple. Then essentially we'd have a condition number of approximately 1. And this will in turn give us an optimal convergence rate for gradient descent. So this is where this idea of preconditioning comes from. So like, and it also maybe more importantly tells us that our architecture, if you want to use PINNs, you should probably choose it based on the problem at hand. And this is maybe why we're seeing like, okay, we have one particular neural network in one setting that's solving this type of equation, another in another type of equation. So now we can go back to the different tricks and techniques that I introduced before, and we can try to see, like, under this light, can we gain some insight on why they work. So let's look at curriculum learning. We saw that the condition number of the linear advection problem was related to the constant velocity to the square. And so then it makes sense that if we're starting from a smaller velocity, then our condition number will improve quadratically. And then we can solve our equation, and then we can progressively make beta larger. Now, let's look at domain decomposition, or what's called sequence-to-sequence learning, where we first consider some solving the equation for some small time, 0 to delta t. And by splitting our time into n sub-intervals, it's actually like you're sort of changing your velocity. And so it has the same effect. So if you make more sub-intervals, you're going to reduce your error quadratically as well. So this is why we observe the similar results, I think. And obviously, the second optimizer, considering a second order optimizer, we can also, since for our linear models, in this case, the Hessian of the loss, it's exactly corresponding to this matrix A. Well, Newton's method would give us a perfect preconditioning, because we'd be multiplying the gradient by A minus 1, and therefore our new effective matrix would have and our conditioning problem would be the identity matrix. So the condition number of the identity matrix would be effectively a 1. But obviously it's a trade-off, because computing the Hessian is very, very cumbersome in practice and very costly. And so what people do is, in practice, and is just saying, okay, if you have a good estimate of a minus 1, then you can just plug it into there. And then hopefully you'll get something that works. So this partly explains why second order optimizers or approximate second order optimizers like Atom or LBFGS work better. Okay, so now let's go back to the Fourier features. And in the case of the Fourier features, we can also see, okay, what does the associated kernel look like? The NTK kernel. And the NTK kernel will actually effectively tell us which functions we can represent. It turns out that this kernel is going to be a stationary kernel, which means it's going to be a function of x minus y. And we're going to have this h here, which is actually going to be, okay, there's a mistake here. There shouldn't be a y, but h of x, which actually corresponds essentially to a Dirichlet kernel. So this is going to be like, this sort of this sine of t divided by t. And essentially, since we're going to evaluate it at x minus y, well, this kernel integral operator is actually just going to be a convolution with a certain kernel. And this kernel is going to be the Dirichlet kernel if we have our frequencies which are integers going from 1 to n. And if not, well, we can see how it's going to specifically penalize certain frequencies based on the distribution we're going to sample the bees from. Is this clear? Any questions? No? Okay. Yes? Maybe? No? Okay. Okay. Okay, so yeah. So now I'm done. And just to conclude, we saw different PINNs techniques, different tips to try to get the training loss to 0. And because training error is usually the hardest to minimize. And this is due to the fact that the training problem is inherently ill-conditioned. And then the question is, based on this insight, can you actually develop methods based on preconditioning ideas and numerical analysis in order to train PINNs more efficiently? But what it also tells us is that there's no general recipe, because ultimately the solution is going to be PDE dependent. And maybe because of this, we can actually bring in tools from numerical analysis, and maybe that will help us if we want to solve PDEs using neural networks. Or more generally, just this applies more generally, just including any loss that incorporates a differential operator. The same insight applies in the same way. So yeah, thanks for listening. And yeah, if you have any questions, don't hesitate to tell me.
Thank you, Em, for a wonderful talk. So I'd like to request anyone, if you have any questions, to unmute yourself. But otherwise, so previously, I have a question about I think the 2 sets of results that you had shown through your experiments, numerical experiments, I would say, with linear advection and I think the equation before that with the forcing term. So here you're saying that the conditioning of A is dependent on k power 4, where k is your frequency, I believe. And now if you go to the linear advection in the next slide, I guess, you had mentioned that it's dependent on the parameter beta, which is your constant speed for linear advection. So is there any specific way to decide, or is it something that you came after, deriving it based on the given PDE that you have? So how exactly is it like? So if you have a linear advection like this, and if you had something like a forcing term or something on the right hand side, how do you decide your conditioning of A? Like, so basically, I'm just talking about the observation that you're giving at the bottom.
Yeah. Okay, so this is done just by calculation. So
Right. Okay.
you have to perform the calculation for every for everything,
Yeah. Okay. Okay.
every specific context. But then based on this insight that you have this D star D that you consider. But yeah, we had to prove this for every specific context. But here
Okay.
it's quite simple because we're making use of the fact that the basis is orthonormal. So
Okay.
then we
Okay.
don't have to consider this T. And then ultimately it just corresponds to the spectrum of this Hermitian squared operator. And in this context, if you have your so this, but it was easy for us in our case because by taking the Fourier series or the sines or the cosines, they're eigenfunctions of this operator here.
Okay.
So things are quite nice because then you end up with not like they're not eigenfunctions in the sense that they don't have, like, when you apply them, you apply D, they're eigenfunctions in that sense. So you're gonna have just a very nice diagonal matrix for A.
Right. Okay.
So this is going to be quite nice, but then so obviously the example is chosen in a specific way so that the explanation of the
Yes.
the method is simple and the insight is palpable.
Right. And also, if you go to that experiment, the plot that you had shown before, so if I were to zoom in to those curves on the top, something that I must expect is that the 95 will be having the maximum error, and as you go down your Fourier features, you should expect better and better error. Is that something that you can also generalize?
This is with and without preconditioning, right? So
Yeah.
they're two different plots.
No, I'm just talking only about the cluster of plots on the top. So within that cluster, so within that cluster, so as you go on reducing your Fourier features, you must expect better and better error in your training. Is that right?
Exactly.
And
Yeah,
that is
yeah.
that is applicable for any equation that you have, or for most of the equation.
Linear.
Linear. Okay. Okay.
So yeah, they have to be linear equations, and then it has to reduce effectively the condition number, I guess.
Right. Okay.
And then that you have to prove it based, but then I guess most you probably need a specific I guess it's not always the case, but then if they're diagonalized in Fourier, then you're good. Yeah, I guess.
Right. Okay. Okay. Thank you.
Emmanuel, just one question. How do you think that this will this idea be applicable to the high dimensional linear PDEs? Say, for example, again the Poisson equation in high dimensions. So basically, your D star D will change, right? And how do you see it will affect your conditioning? The conditioning of D star D times the T matrix. Sorry, T operator.
Yeah. So that's a good question. So what we do here in this particular context is that we derive as a simple example, a simple ansatz. And this ansatz is a linear ansatz. So it suffers from any linear ansatz, and like it would take, if you consider the Fourier features here. So okay, so this is in 1D. It's simple, but then the amount of basis functions that you have increases exponentially in the dimension, right? So here we had this 2D case. So then we had to adapt our basis functions, just taking like a sort of like a product. And so this simple example doesn't necessarily translate to this very high dimensional setting in which you can't grid the space, or you can't consider not grid the space, but you'd need like an exponential amount of basis functions in order to tackle each direction, right?
Okay.
That being said, you still have this D star D doesn't change, right? Because it's still the Poisson, right?
Yes.
So you still have the same insight.
Okay.
Now, I'm guessing your question.
It's just a question of choosing a basis function in high dimensional spaces. So for example, if I have a 100-dimensional space, and instead of solving that equation in one shot, and I'm just using the batch size of, say, 2-dimensional, then I can use this analysis, right? Because at one, so for example, for a particular number of epochs, I'm just solving a 2-dimensional problem and then switching it to next 2-dimensional, randomly chosen. So I can still use this analysis, right?
Yeah. So even in the high dimensional setting, you can still use exactly the same analysis still holds, but then you just have to choose appropriate basis functions. And then you need to, so if the appropriate basis functions that you choose, if you actually choose a basis function, then they're orthonormal, then everything exactly holds, and this T is equal to identity. It's just that in maybe 100 dimensions, it becomes obviously cumbersome to handle all those basis functions. So then maybe you'll resort to another method, which is not necessarily explained by this PD linear setting, right? Where we have a linear ansatz. So maybe like here's where we can actually observe like maybe some departure from our theoretical setting in the high dimensional sense, where our neural network can actually effectively solve the Poisson equation in high dimension, because there's something that's the higher order effects in the dynamics actually help us there. And the higher order dynamics is not something that we're modeling here. Okay. So this is a caveat maybe of the analysis, and maybe a potential interesting avenue for neural networks which are known to function quite well in high dimension. And there's some potentially low dimensional subspace that we can actually leverage.
Okay. Yeah. Thanks.